Hey folks, this is Janal here. I just wanted to share some updates and insights on why I've built this seismic response simulator and then how it actually works and how can you actually take advantage of it. Um, so the only reason I built it because instead of just me playing with something internally, I thought uh, this can benefit students, this can help professors that are teaching in schools, universities, and even young folks, right? Like that are trying to get into or interested in buildings in general. Um, so this is kind of a pseudo realism, is what I'm calling it. Like it does incorporate more or less the physics that goes behind the numerical simulations. And then it has also incorporated some of the numerical methods that we use to analyze and evaluate any particular structure. And there are certain realistic parameters that are baked into this particular tool that you can play with and toggle to develop more understanding on how the building should behave. So I've just added few different famous earthquakes that we have all known about, and each record is a little bit different. So with the same building parameter, you can toggle through different records and then see how that building kind of performs under those records because every record has a different kind of properties and that affects buildings very differently. So what you can do in this particular tool is you can just select any of your frame that you're interested in, select number of stories and all the geometrical stuff. But what are more important parameters are kind of column stiffnesses, rigidity of the frame elements. Then you have the ductility and some additional rooftop masses, right? So sometimes you have heavy equipments, heavy water tanks and whatnot at the roof, so you can toggle that parameter and see the building behavior, how it changes. But what's more important per se is understanding like how the building is behaving and also the insights that the tool is giving you, right? So it is kind of taking some preliminary fragility curves, like the basic level fragility curves from FEMA P58 as well, which just looks at, okay, what's the drift fragility for any general frame building? So it's not even discretized between like a moment frame, shear wall, brace frame building per se. It's just using like a very average fragility curves that's kind of give or take within the neighborhood or the bounds. For for building systems like URM per se, it has like a very different understanding and it's not kind of giving us the FEMA P58 collapse fragilities. It's just giving us insights that how we usually tackle unreinforced masonry. That's like by adding supplemental strength and other lateral elements to control the drifts and then reduce the stress on the unreinforced masonry so it doesn't collapse. So that's just a high level overview. And then what this has baked into this is kind of a elastoplastic curve, so it doesn't have any strength or stiffness degradation. I was just trying to keep it simple because again, the idea is to get a high level of understanding of how a building performs in seismic and how can you change different parameters. So what do I mean by that? Um, Simply, I'm just gonna maybe just shake this building in a Northridge event, right? So what's gonna happen is, okay, now the building has collapsed, right? So once this kind of animation stops, which is kind of a little bit okay, but then it gives us like an idea of like, okay, what happened with this collapse, and then what kind of system it is, right? So we are looking at the brace frame. So it's saying like, okay, right now based on the seismicity, our ductility is too low. So maybe just increasing the ductility could be more effective than anything else, right? Which is what we know. Adding more ductility to an extent helps reducing the seismic inertial accelerations, right? So now you can just add that ductility and see how the building is behaving. Oh, it's not failed yet. It may or may not. We'll see, right? So okay, so it seems like adding more ductility did help because it can accommodate that drift. And then with those drift, right, like you can see that, okay, how it's distributing the plastic mechanisms across the building height and the bottommost story is under the most kind of demands. And then it's also giving us a residual drift assessment, But it's saying that, okay, the model has predicted about 41% and the FEMA inferred is like 0.87%. And based on FEMA, the probability of demolition of this building is like 32%. So then it also kind of gives us an explanation of why the model over here is under predicting the drifts. That's because of the bilinear no degradation backbone hysteresis, right? Versus real backbones have pinching effects and then buckling effects and whatnot, right? So there is strength and stiffness degradation as well. And with each cycle, you get like loss in the energy dissipation in a lot of elements that we use for seismic resistance. So that's not captured. So that's one difference. And then it also again gives us a little bit more insights that, okay, your residual is high, so maybe you can increase the strength, right? And then you can increase the brace capacities over here and then shake it again. And then you'll see like, okay, now the performance is a lot better. Now you are not going that much into the residual territory. Your peak drift is also kind of coming down because yes, your capacity has kind of gone up, right? So this is how you can kind of play with this particular tool just to again develop some insights, develop some understanding on how building systems are behaving, right? So now you see it's a little bit funny, right? So the model is predicting a residual of 64%. That's based on the story with the most like the peak drift. And it's kind of taking the oscillation of that story beyond the earthquake record and seeing how much residual, like where the residual is kind of converging to from a mean standpoint. And FEMA P58 is more like based on the peak drift values, it has inferred like, okay, it has about 0.57%. And again, it's not specific to brace frame, right? So that's the other difference. So you can play with this tool and then run different sorts of simulations under different earthquake, right? And this will give you more insights on like, okay, if I have like different earthquake, different properties. So you can see here, right? So the response spectrum for Mexico City, because of the basin effects, is kind of peaking at around 2 seconds. Versus if I just go back to the Northridge, it's more of a traditional spectral acceleration curve that we are all used to, which is at 1 second. And again, in Northridge, 1 second was pretty high because of the pulse effects as well. Anyways, so what beyond that, what I've kind of just added is like um, the history about the earthquake. You can just learn some additional information on what happened in the building codes after this particular earthquake. So Northridge is famous for the steel moment frame connection failures and the soft story mechanisms. So that's kind of added, and then how the building code evolved from this earthquake onwards, right? So some history lessons. Um, So as a part of the SE Playground itself, I decided to build something called a structure lab. So in structure lab, what you can do is like play with any random structure you create. You can create like a cantilever bridge system. You can create I don't know, like a telecommunication tower and shake it over here. And then you can also kind of have the ability to maybe add some seismic joint masses. So let's say I just want to add some 75 kips at each joint. So you can add that. And then you can say like, okay, I have a fixed frame or a pin truss. So let's say I have a pin truss system over here. And then you can just select an earthquake, make it more reasonable based on the peak ground intensity that you're interested in, and then just shake it, right? So based on that shaking, based on the strength and the stiffness of each element, you'll get to know whether the system is collapsing or not. In this case, it's pretty rigid, it's pretty stiff, so it's kind of working fine, right? So you can do whatever you want with this particular what I call it is like free play. But then if you want to do like more realistic lessons, you can also build a system like here, right? A taller tower which is connected to a podium tower with just a transverse slab, right? So in this instance, it what we are interested in is how this additional kind of like discontinuity affects the members that are localized to that discontinuity, and then how this particular member that's connecting the two towers together is going to affect is going to be affected by everything, right? So you can just say, okay, I'm just going to shake this, right? Like, oh, that podium slab immediately collapsed, and then my entire building collapsed because maybe there was something dynamically right? It was just meant to work together, but now it cannot, right? So you can think about, okay, what if I just maybe scale up my strength of the podium slab and then shake it again, right? So you can shake that again and see whether it's working or not, right? So it seems like it's going well. Okay, it went up to collapse prevention, but it hasn't kind of fallen yet, right? And then my podium slab kind of stayed elastic. So all I did was increase the strength of the podium slab, which means I'm accounting for those overstrength forces transferred from this taller structure down into the shorter structure. Because that stayed up, that didn't collapse. That means both of my towers were acting together, and then they were able to survive this particular shaking, right? So you can bring these kind of textbook understanding into more of a realism and see what the actual documents, the books, the building codes uh, actually mean by some of those provisions over here, and why do we follow those provisions. And what's important to see is, right, like this entire thing below podium slab, right, none of that even reached life safety, none of that is orange, but then everything above the podium slab in this tower went up to like orange and red, which is life safety and collapse prevention, right? So this is a significant stiffness discontinuity, and then this upper portion was almost acting like a secondary building. And when you actually shake it as well, right, what you'll notice is the period of this, how it's influencing the higher mode responses of the structure over here. So it's that combined period which is kind of throwing more amplification in the taller structure up here. So all of these kind of what should I say, the building behavior, the behavioral level understanding can be unlocked by playing with a tool like this. And it's not that time consuming to modify few parameters here and develop that understanding, develop that intuition per se, right? And then learn more about how you can design more resilient structures for the future. And that's my whole point in building this and developing this, is to spread the knowledge, spread what I've learned so far, and then just bring everyone together for more and more kind of a resilient infrastructure development for the future. Um, if you have any kind of suggestions for improvement, feel free to let me know. In this, I just have built on the during my spare times, but would love to make it better if anyone needs anything more. Um, so yeah, thanks for listening to some of my discussion over here.